Okay, so let's recap what we have done so far. Firstly, we talked about integer exponents. We said that integer exponents are where the exponents are integers, and we've defined what integers are in the number systems module, so we understand exactly what that is. We then moved on to exponential notation and discussed the basic structure of a term that has a base and an exponent, right? And we said that it's used for communication, so we all have to understand exactly what we are writing. Then we talked about the placement of the negative, and we said that when we're dealing with even powers, it's very important that we know exactly where the negative is placed, because in one case, even though we have an even power, and even though an even number of negatives will, when multiplied out, will give you a positive, there are instances where you could have a negative, if placed in a specific position, can give you a negative, like this case here. And there's an instance where if the power is applied to the negative, then we have a positive. So that's very important, knowing where the negative sign is, right? And if the power is applied to the negative itself. If it's applied to the negative, then you have a positive answer. If it is not applied to the negative, like this case here, then you have a negative answer. We've discussed in detail and quite extensively what exactly a square root and a cube root is. I've discussed extensively about the positive and the negative square root, and I discussed extensively the difference between being given the square root and using the square root. Then lastly, we discussed the comparison of exponents, right? So the three different cases that you can get when comparing exponents, and how you basically work with those three different cases. Now I'm going to discuss the exponential rules, right? So we're given exponential rules exactly like the properties that I gave you for fractions. There's certain properties that you can utilize with fractions that can speed up the process when working with fractions. It's the same idea with exponents. There are certain properties that we can use, or certain rules that we can use when working with exponents, so that we can speed up the simplification process. After all, the only two things that we do in maths is simplify and solve. So if we can find rules, then we can utilize the rules. Again, as I said repeatedly, these rules have been thought out quite deeply by brilliant minds. So we do not have to question the rules. I will give you a logical proofs as to why the rule works, but it's not actually something that formal. It's not an actual formal proof, but it's just so that I can show you that it logically, how it pans out logically. Okay, so that's all you need to know. But remember, do not question the rules. And also remember, we do not need to know the names of the rules, as long as we understand its function and its purpose. Okay, so if we can do that, then we literally have everything that we need to solve exponential questions. Okay, for the exponential rules, let's just review and recap the exponential notation. The number at the bottom is the base. The number at the top, the superscript, is what we call the power, exponent, or the index. The base is the number that is being repeated. The power, exponent, to index tells you how many times the base is being repeated. Okay, so let's look at the first rule. X to the power of m times x to the power of n is the same as, see the equal to sign, means is the same as. So this is the same as this. Is the same as keeping the base and just adding the indices. So for you to formally write this down, whenever multiplying terms with the same base, keep the base and add the indices. So that's the rule. Whenever multiplying terms with the same base, keep the base, I kept it, and add the indices. We added it. Let's understand where this rule comes from. The 2 to the power 3 times 2 to the power 5. Let's expand it. It's 2 times 2 times 2, 3 times. 2 times 2 times 2 times 2 times 2. That's 2 multiplied by itself 5 times. If you count the number of 2's here, we have 8 2's. So we have to bring it back to exponential notation. It is basically 2 to the power of 8, because we're multiplying 2 8 times. I can go from the question right to the answer. I can bypass the step here by expanding, by just following the rule. Okay? But it's very important to note that the base has to be the same. In order for you to utilize this rule, the base has to be the same. Okay, so rule number 2, the quotient rule. The quotient rule basically states that whenever dividing terms with the same base, subtract the indices. Right? So let's look at this. Let me expand this. If you have 2 to the power 5 in the numerator and 2 to the power 3 in the denominator, so 2 to the power 5 will be 2 multiplied by itself 5 times. 2 to the power 3 will be 2 multiplied by itself 3 times. Because the numerator and denominator has common terms, we can start cancelling them. How many can we cancel? 3. Because we have 3 2's at the bottom in the denominator. So that leaves us with 2 times 2. And if you have to put that in exponential form, it'll be 2 squared. However, I can go from here to there and bypass these 2 steps by just following the rule. However, again, we must see that the bases have to be the same. So if you have to state this rule verbally, it is whenever dividing terms with the same base, keep the base and subtract the indices. So it's a very straightforward rule if we understand how to utilize it, right? Now what I'm going to do is I'm going to discuss something else that basically ties in with the whole quotient rule, right? It ties in with the quotient rule, and it's called negative exponents. Okay, it's called negative exponents. So let's read the negative exponents. You see, we never ever deal with negative exponents in maths. And if we do, this is how you make it positive. You make a negative exponent positive by swapping its position from the numerator to the denominator. And if it's negative in the denominator, we take it to the numerator. Because see, any number can be written over 1 as a fraction. You understand? Right? So 2 written as a fraction is 2 over 1. X to the power minus m written as a fraction is x to the power minus m over 1. So that's how we can write it as a fraction. And if you can see it's in the numerator, then we can swap its position from the numerator, put it to the denominator, and make it positive. Very, very straightforward idea, right? Now, let's do a question here, right? Let's do a question. So this is our quotient. We're utilizing the quotient rule here. Let's say that we have x to the power 12 over x to the power 6. That'll be equal to x to the power 12 minus 6. And that's how we get x to the power 6. If you want to see it more clearly using negative exponents, then what we're doing here is we're basically taking the x to the power 6 to the top. However, when we take it to the top, we have to make it negative. Right? Because we swap its position, it becomes negative. So basically, we have x to the power 12 times x to the power negative 6. Then we multiplying powers of this. Then we are multiplying terms with the same base, so we can add the indices. So it'll be 12 plus in brackets minus 6, which is 12 minus 6, which gives you x to the power 6. Right? Just utilizing the negative exponents rule. Now that's very simple. However, what happens if we have x to the power 6 divided by x to the power 12? Then that'll be x to the power 6 minus 12, which is x to the power minus 6. And then we have to make it positive by saying 1 over x to the power 6. It's easy, right? We can do that. However, with more longer format questions, see now I'm looking at these rules in isolation. When we start doing more miscellaneous questions and longer format questions, it's sometimes better to just go from here to there, straight to the answer. So how do we do that? Just remember this. You always say it's the bigger exponent minus the smaller exponent, and the term goes in the position of the bigger exponent. For example, here, I'll say it's the bigger exponent minus the smaller exponent, and the term goes in the position of the smaller exponent. So in this one here, I'll say bigger exponent minus smaller exponent, so it'll be 1 over x to the power 12 minus 6, which will be 1 over x to the power 6. Can you see that? That's how we do it, straightforward. And if you want to think of it in a more visual approach, if you want to see it in a more expanded approach, it's exactly what I did here. You have 6 x's at the numerator, and we have 12 x's at the denominator. You'll have, so if I have to expand this, will be x times x times x times x times x times x over. And you'll have 12 x's in the denominator. And then you'll have 6 common factors, so you'll start cancelling with all of the x's. Eventually, you'll be left with 6 x's in the denominator. So that's how you can start thinking of it. That's the reason why we say it goes in the denominator, because you have more terms in the denominator than you do in the numerator. So it has to go in that position. Okay, so you'll have precisely 6 x's in the denominator. Very straightforward idea, but it's important that we understand it now, because when we start doing more complicated examples, we can go directly to the answer without actually working with negative exponents, because eventually we have to convert negative exponents to positive. So that's how we're starting to think a bit more faster in terms of these questions, right? So let's do rule number 4. Okay, rule number 4, power to a power rule. Write this down. Whenever raising a base to another power, keep the base and multiply the indices. So if you're raising a base to another power, so this base has a power already, but we're raising it to another power. You keep the base and you multiply the indices. So this is the way you think of it. You see in the bracket here, we're saying that 2 to the power 3 is repeated how many times? 2 times. You see 2 squared is repeated how many times? 2 times 2. 2 to the power 4, 2 is repeated how many times? 4 times. Can you see that? So here, 2 cubed is repeated how many times? 2 times. So that's the reason why I have 2 cubed times 2 cubed. Do you understand that? That's how we actually decode this entire idea. And then 2 cubed times 2 cubed is 2 to the power 6. Whenever multiplying terms of the same base, keep the base and add the indices. However, I can go directly from here to there by doing what? Multiplying the indices. Straightforward. Right? Now, the rule can go in the reverse direction. As I've stated, under the properties of fractions, I said that sometimes, not all the time, in maths, we can go in the reverse direction. Right? So the rule can apply both in the forward direction and in the reverse direction. So basically the way the rule is stated now, if you got this, then you do this. I'm asking you, if you have this, can you do this? Yes, you can. So this is what I mean by stating the rule in the reverse direction. So if you have x to the power m times n, and remember, according to the commutative law, 1 times 2 is the same as 2 times 1. We said that multiplication is commutative, meaning that the order does not matter. So what we can do is, we can write it as x to the power m raised to the power n, or we could write it as x to the power n raised to the power m. Okay, that's very straightforward. Okay, let's do rule number 5. Okay, let's look at rule number 5. Rule number 5 is called product to a power rule. Okay, so basically write this down under the product rule. Whenever raising the product of two different bases to the same power, then you can raise each base to the power. So basically what we are doing here, we are distributing it into the bracket. Okay, now that's in the forward direction. If you are given this, then you can do that. Now I'm asking you, if you are given this, can you do this? Yes, you can. So if you're given the product of two different bases raised to the same power, you can extract the power and raise it to the product of those two bases. So you can extract the power and raise it to the product of those two bases. Right. So let's see a visual example of this, right? So see, 2 times 3 to the power 4 is equal to 2 to the power 4 times 3 to the power 4. If you have 2 to the power 4 times 3 to the power 4, then that's equal to 2 times 3 raised to the power 4. Note how I'm stating this verbally, right? Note how I'm stating it verbally. Now look at this example here. I can do this in one of two ways. The second approach is something that I will show you at the end of the video. However, looking at it from now, using this rule, just using this rule alone, this is what I can do. I can say it's 2 times 3 to the power 4 over 6 squared. Think about that. So now, because I saw 2 and 3 and I saw 6, then I know that 2 times 3 is 6, and I know that the powers are the same. I can extract the power. Right, so now I have 6 to the power 4 over 6 squared, so that gives me 6 squared. The second approach to solve this problem is the approach that I will show you at the end of this module. But for now, can you see how we can start thinking creatively and utilize these rules, right? And this is why with exponential rules, the only problem I see with the way it's taught, it's that they don't ever tell you that the rule can apply in the reverse direction. They don't ever tell you that, I promise you, right? So that's the reason why I'm stating it like this. See, this is the same as this, right? But sometimes when you go up to university level, you'll see that the rule does not always go in the reverse direction, right? It does not always go in the reverse direction. That's why we have to be very explicit when we are using these rules. Okay, let's do the last 4 rules, and then we can conclude the exponential rule section. Very simple rules, okay? Okay, quotient to a power rule. Quotient to a power rule. Let's write this down. Whenever raising a quotient to a power, so whenever raising a quotient to a power, raise both the numerator and the denominator to the index. So whenever raising a quotient to a power, you can raise both the numerator and the denominator to that power. So what you'll write here, again, the bases must be different. So different bases. Now listen, hear me out. The reason I'm stating this explicitly is for one reason. If the bases were the same, would there not be 1? Would there not be 1 in the brackets? So that's the reason why when you're simplifying, it's better when you're simplifying, it'll be more applicable when the bases are different, because that's when you'll only have to simplify it. If it was 1, then it's a straightforward question. Do you understand that? That's why I'm stating that the bases have to be different. Right? If the bases are the same, yes, obviously. You can go and distribute the 2 there, distribute the 2 there, you'll be the same. Understood? Understood? Right? Right? Even with the product rule, if it was 2 times 2 raised to the power of 4, yes, you can distribute the 4 to each of the terms. But then why do that? Why do that? Where is the simplification needed there? Right? You can just say it's 2 squared raised to the power of 4. Right? That's just the power to a power rule. Why are we don't actually need to do anything, because we can simplify this using rule 1. So it's more applicable, more useful. It's more useful when the bases are different. Understood? So let's look at this question. Yeah, okay, I hope you understand that. So that's the reason why I'm saying it's more useful when the bases are different. Right, so here, if this, then that is the, can I use the rule in the reverse direction? Yes, I can. So if you're given 2 different terms raised to the same power, you can extract the power. Right, so if you're given 2 different terms, if you're given the quotient of 2 different terms raised to the same power, you can extract the power. So this is the quotient of 2 different terms raised to the same power, I can extract the power. So if I look at this now, I can go in the reverse direction. So looking at this, using the rule, why does the rule make sense? See, 2 to the power 3, this base is repeated how many times? It's repeated twice. Right? It's repeated twice. So it'll be 2 to the power... See, this base, 2 over 3 is repeated how many times? It's repeated twice. That's what the 2 outside is telling you, that the base is repeated how many times? 2 times. So that's 2 over 3 times 2 over 3. And if you have to simplify that, that's 2 times 2 is what? 2 squared. 3 times 3 is what? 3 squared. You can go directly from here to there by just distributing the power. So 2 to the power 2 over 3 to the power 2. Very straightforward. Let's look at the next rule. Okay, something else that I want you to take down, right? Under negative exponents. Because this is a very important rule. You see, when you give a negative exponent, let's say you're given x over y, and you have raised to the negative 1. You have this fraction raised to the negative 1. So this is more like a variation to the rule. The standard rule applies, but how can we expedite the process given a more complicated question using the actual rule? You see, the way you can make this exponent positive is by swapping the positions of the numerator and the denominator. Why? What happens? If this goes to the top, this becomes y to the negative 1. If this x goes to the denominator, it becomes x to the negative 1. And this here is all raised to negative 1. What I can then do is, if you follow this rule here, the quotient to a power rule, if you follow the quotient to a power rule, right, I can extract this negative 1, right? So I can say it'll be y over x to the power minus 1 multiplied by the minus 1 that was outside. Multiplied by the minus 1 that was outside. So if I have to put some color to this, it'll be multiplied by negative 1. Let's say that negative 1 there was purple. It was the negative 1 from the question. And now what you can do is, negative 1 times negative 1 is a positive 1, so it's y over x. So simply by swapping the numerator and the denominator, we can factor out a negative 1 and make the exponent on the outside positive. So if you have to give you a more complicated example, let's say that you were given, now please take this down, let's say you were given x squared over y to the 4, right, all raised to the power negative 6. Then I can say y to the power 4 over x squared is equal to 6. Right, just by swapping the positions, you can factor out a negative 1. Right, so they do not necessarily have to be 1 and 1. They can be any number, as long as when you swap the position, you are in fact taking out a negative 1, but you must multiply the negative 1 by the number that's on the outside. Now, we can go in the reverse direction, but that's not actually useful. Because why are you making an exponent negative when the entire purpose, the negative exponent rule, is dedicated for making exponents positive? So therefore, it's not a very useful rule when we are trying to go in the reverse direction, but in the forward direction, it's very useful. Now, that is not to say that the rule in the negative direction does not work. It does work, but it is not useful. So I can go from here to here. I can make this exponent negative, but it is not useful because our aim in maths is to simplify and solve. In the forward direction is when the rule is actually useful. Okay? Let's look at the next 2 rules. Raising a non-zero number to the power 0 is what? 1. So as long as the number is not 0, then the answer is 1. Now 0 to the power 0, when you do more complex, when you go to higher grades, there's no actual value for 0 to the power 0. Right? There's many values that you could have. It doesn't have a single value. But for now, you just need to remember that you're raising a non-zero number to the power 0, it will be 1. Raising any number to the power of 1, any number, there's no restriction, it'll be that number, right? It will be that number. Right, now let's look at the next set of rules. Right, let's state this here. These rules apply to both cube roots and square roots. So it applies to both cube roots and square roots. Let's look at the first rule, the product rule. So the square root of a times the square root of b is equal to the square root of a times b. Right? Note how I'm stating that verbally. The square root of a times b is equal to the square root of a times the square root of b. Notice how I stated that verbally. See, if I'm given this, then I can do that. That's basically what we're stating. And if I'm given this, then I can do this. Do you understand that? That's how we can do it both in the forward and reverse direction. Again, as I said, this happens not all of the time, sometimes. So let's say we're given the square root of 2 times the square root of 3. That's equal to the square root of 2 times 3, which is the square root of 6. Now let's look at a neater example. You have the square root of 2 times the square root of 2 is equal to the square root of 2 times 2, which is equal to the square root of 4, which is equal to 2. Can you see how we are given? These are what we called surds. Remember, these are irrational numbers. On their own, we can't actually simplify them now, isn't it? But see, when we multiply them, see what we get in the radical sign. What we get what's the radicand? 4. Can you see that the radicand is 4? So therefore, it simplifies to 2. That's a nice, neat example that you can see. Lastly, let's look at the quotient rule. The square root of a over b is equal to the square root of a over the square root of b. That's in the forward direction. Does it work in the reverse direction? Yes, it does. So if you're given this, you can do that. Now, if you're given this, can you do that? Yes, you can. I am telling you, you can, right? So how would that look like? See, the square root of a over the square root of b is equal to the square root of a over b. So let's look at some examples here. The square root of 1 over 2 is equal to the square root of 1 over the square root of 2. That's not a very nice example. Let's look at this one here. The square root of 1 over 4 is equal to the square root of 1 over the square root of 4, which is equal to 1 over 2. So given this here on its own, if you didn't know the rule, you'll think that we cannot simplify it. But according to the rule, we can by rooting the numerator and rooting the denominator. Right. Something else that we can do with this product rule, It's that, let's say you're given the square root of 8, I can actually simplify this. Because if I know that there's a perfect square, what are the perfect squares? 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, and 144. Now I know that there's a perfect square in this, so I can say that this is actually the square root of 2 times 4. And then I can say that this is actually the square root of 2 times the square root of 4. And then I can say that it's 2 square root 2. Can you see that? So this 4 here simplifies to the 2 that's on the outside, multiplied by the square root of 2 here, which is 2 root 2. And this is basically how you simplify radicals. Now, this is an idea that we will talk about next year, but the radical is basically the square root sign. So when you're given radicals, you can simplify them by just employing the product rule. But I'm just giving you a bit of the foresight. It's not something that you have to know, but I'm showing you how you can go from year to year utilizing the product rule. However, you need to remember your perfect squares and your perfect cubes. So let's say we were given the cube root of 54. If you're given the cube root of 54, and if you could see that 54 can be re-expressed as 27 times 2, the cube root, then we could say that this is actually the cube root of 2. It's actually the cube root of 2 multiplied by the cube root of 27, which will give you 3 cube root 2. This is not a complicated example. And obviously now, because we are using just these basic rules of products and quotients, we will start using more rules dedicated to solving these problems, okay? So there are rules dedicated for solving radicals, but I'm showing you utilizing the rules of grade 9 and 10, how can we solve radicals, right? So that basically covers all of the exponential rules. Again, notice that I said here, same base, different base. Again, like I said, these rules will apply even if the bases are the same. But it is more useful when the bases are different. It's more useful when the bases are different. Because if the bases were the same, then we could have used the product rule, where we said 2 times 2, the bases are the same. Whenever multiplying terms of the same base, what do? add the indices. Can you see that? Or what you could have done was you could have said, see, 2 times 2 raised to the power 2 is also 2 squared times 2 squared. I just distributed this in. And 2 squared times 2 squared is what? 2 to the power 4. Here too. See, whenever raising a power to another power, multiply the indices. Can you see both gives you the same answer? That's why I'm saying just look at it in terms of it having different bases, because then it's more useful. Because if it was the same, we could have used rule 1, the product rule. Right, that's why I explicitly stated that the bases must be different. Right? But they do apply if the bases are the same. But it must be different because it's more useful. Okay, so that's about it for the exponential rules. Okay, so now